In this section, I'm going to introduce you to the technology behind connected devices or the things in Internet of Things. You may realize that some of the ideas I present in this section you may have seen in other sections as well. However, the key difference is that in this section I'll be focusing or looking at these connected devices from human computer interaction or the human factors design perspective. The connected device or the things we come across in Internet of Things can be broadly divided or separated into 4 different categories. First one is the multipurpose computers. We all have seen them, we all have them. The second category is specialized embedded devices. These are, for example, you will see in vehicles, heating systems, remote control door locks, blinds, and many other places where there is a computational device focusing on a specialist task. Then you have the connected sensors. For example, security sensors such as motion sensors or contact sensors. They are very much focusing on sensing tasks and then emitting some kind of results to the control center. Finally, you have the passively trackable objects, which you see NFC, near field communication, or the RFID tags, which are commonly used in tracking and supply chain type of applications, but they are commonly used in some toys and household items as well. For example, you will see NFC trackable objects in key tags of your vehicle, which helps you to find the keys quite quickly, or to track your pet easily. When we compare these devices, we can clearly see the differences in terms of user interaction, functionality, and processing. So if we compare the user interactions, the multipurpose computers, they have rich onboard interactions, including the capabilities with inputs from keyboards and screens and other multimedia devices. But when we move to specialized embedded devices, these inputs are very much limited, and then most probably you will be interacting with them with maybe very few hardware buttons or kind of tangible interface, or most likely through a mobile or a web interface. Connected sensors are usually always connected through a mobile or a web applications, and similarly the passively tracking objects are also connected or interacted through mobile and web applications. Functionality wise, we previously discussed that multipurpose computers are generalized. They are capable of performing more general and wide variety of tasks, but specialized devices are specialized and optimized to perform a particular task or a very few tasks, but they're very good at those tasks and very optimized and resource efficient on those tasks. And then the connected sensors are pretty much a single task, which is sensing, and then the trackable objects are used for identification only. In terms of processing, multipurpose computers have significant processing capabilities. Specialized embedded devices have reasonable computing capabilities, but they are focusing on a very particular task, and also they might be depending on the cloud services. So they might be do some processing on the devices and sending to other device for the further processing. Regarding the sensors, most of the time, other than a simple aggregation, most of the data is sent to the cloud for the processing. And then the tracking objects, they are basically very little processing. They would sending identification information to the cloud, and the cloud will do all the processing of combining different trackable objects together, or mapping features or any other functionalities on the cloud. I will go through these different categories one by one over the next few slides. So the first category we identified is the multipurpose computers. So these are the traditional computers which were used to browse web, watch movies or play games. They have very rich interaction capabilities in terms of screens, audio, touch input devices, gesture control, voice control, and many more. They also contain very powerful microprocessors with external chips to control memory and peripheral devices and networking. So these devices, we don't think them as IoT devices, but we more often use them as a proxy to communicate or interact with IoT devices, because as we discussed before, most of the time the embedded devices or the connected sensors do not have dedicated screens or interaction mechanisms. So we use these multipurpose computers or the devices to communicate or interact with the IoT devices. The next category of devices are embedded devices. In everyday life, all of us have seen these embedded devices all around us, even though sometimes we don't identify them as embedded devices. Almost certainly, we have seen embedded systems in our vehicles, or some of the toys, or the thermostat, or the weight scale we are using in our daily lives. What have IoT changed in this domain is that we are seeing more and more devices where traditionally we did not anticipate any onboard computation or connectivity to happen are now come with embedded control systems into them. So for example, internet connected toys are somewhat relatively new, where the toys have interfaces that can communicate with internet services, and certain amount of computation happens within the toys themselves. Most of these embedded devices are specialized in performing one or few different tasks, but they are very much specified or optimized to perform these tasks in the best possible way. Traditionally, we have seen these embedded systems in more expensive devices or equipment like washing machines, because many years ago, to have an embedded system, it requires a lot of software and hardware development, research, and then be able to add these components, electronic components into devices. Also need to increase the price up to a certain level, because you need to recover the R&D cost and then they recover the component cost. But with the popularity of IoT devices, these smaller embedded devices or the smaller electronic components, the prices went very low, and then it enables for the manufacturers to be able to embed these electronics into any kind of device without increasing the price significantly. And then the IoT ecosystem attracted a lot of developers, and then these developers develop more frameworks that can be reusable and then easy to use. So once it is developed, similar to the mobile app ecosystem, like the APIs and frameworks. So now when you become IoT developer, you don't have to program everything by yourself, but you can reutilize some of the things that other people have developed, or use the tool chains or the integrated development environments to develop your IoT solution faster, which means it reduces the cost that otherwise you need to embed some IoT application on your devices. So because of that cost reduction, manufacturers were able to deploy these embedded control systems into a wide variety of devices. Due to the fact that embedded devices are specialized to do a particular job, they can do the job in a very reliable and very efficient way than a general purpose computer, despite having the less power or any less resources it might have. For example, an embedded computer controlling the car brakes could guarantee it would release and activate the brakes exactly the right intervals needed to prevent you losing the control. For example, most of you have experience in working with general purpose computers like Windows, Mac, or Linux operating system, where you can run multiple applications, but you know that from experience that it is not the best idea to put operating system on a car where some error message or some other competing application trying to get the processing time, while that there is a dog or any other vehicle in front of you where you need to immediately put the brakes on. Most probably all of you have come across the situation. Sometimes operating systems allocate resources into different applications, but they are not very good at understanding what is the most priority in a particular given context, like driving a vehicle. But on the contrary, these embedded devices are basically programmed to do one thing. If it is a braking in a moving vehicle, that would focus on that particular task. So there's no competing applications looking for a processing time in the embedded device, because the entire processing power is dedicated to this particular one task. So that is why most of the time the embedded devices have no operating systems, because you don't need any other operating systems to manage different applications, because there are no other applications other than the particular one that they're designed to operate. And then even sometimes there are some operating systems that are rarely used, and even they use, there are very, very small and stripped down version of a traditional operating system. Some of the embedded devices might have onboard user interaction capabilities. For example, Nest thermostat have a screen and a control. You can touch it, control it, rotate it to interact with the device. So in that case, the particular embedded devices might not be focusing on one task, but very few tasks, but very, very narrow focus. And then I previously mentioned that when you have operating system, it does not guarantee how long it would take to perform a particular task, because there are intervening competing tasks and come and grab the processing time. So there's no actually way to predict when the processing would happen, or there are suddenly some kind of antivirus software will be kicked in suddenly in the middle of where you need to put the brakes on. So traditionally, the mobile phones were considered as embedded devices, but nowadays the modern, traditionally they were used only for taking phone calls or SMS, very few tasks. But now the mobile phones are pretty much general purpose computers. They are designed for run many different applications. So that is something that we have seen changing over time, that started as a specialized device and then moving to as a general purpose computer. In a more futuristic sense, we might see this kind of things happen. So if you like vehicles, now they are not designed by one embedded system, but there could be many embedded controllers working together in a computer system, in a vehicle computer system. But in that scenario, there is a chance that there's a one embedded system which might dedicated to interact with the user, while the other embedded systems are responsible for different tasks. And then at some point in time, this particular embedded system that is designed to interact with the user might become a general purpose computer at that point. From embedded devices to a general purpose computer sits on the a vehicle where it interacts with the users in a much more interactive and a general purpose way, from handling music to showing you maps. So at the moment, some of the vehicles have very specialized devices to show maps, but over time there could be operating system based general purpose systems that would manage all the interaction, including maps, on behalf of the vehicle. Another important aspect of embedded systems are they need to meet far more stringent operating criteria than general purpose computers, especially if they are located in areas that are not easily accessible or controlling safety critical systems. On the other hand, it also need to be able to work on harsh environments. It could be like oil wells or electrical power grids where you have a lot of heat or high humidity or any other environmental factors. It also may need to operate on tiny batteries where the batteries cannot be charged or removed easily, so they has to be run for a longer time. And then also sometimes they need to be run without any errors, because if it is like critical systems like car brakes or nuclear reactors, they need to be work perfectly all the time. They cannot have like a downtime in a operating system or a cloud system. They has to work all the time. And then they potentially should be able to recover themselves from a failure without human intervention as much as possible, because if you are deploying some undersea cables across the ocean, it is not easy to go and fix things. So it's ideally these specialized devices should be recover themselves if there are any unanticipated failures. Another characteristics that we see from the embedded devices is that they are usually forgotten. So when you deploy them, we expect them to work, for example, in boilers or any other vacuum cleaners or devices that we see every day, but we don't necessarily plan to interact with in a similar way that we interact with a mobile phone or any other general purpose devices. So they has to work pretty much autonomously without human intervention most of the time, and then they need to work continuously without any maintenance or rebooting or updates. Finally, we also discussed that most of these embedded devices don't have any control. For example, this particular Tado heating controller, which we show in the image, which does not have any input-output capabilities. So you pretty much depend on the mobile application or a desktop or a web application to interact with that. And also you might notice that in the same kind of devices, like in this particular category, it is a heating controller, which we saw previously, where is a thermostat which did have some level of interaction. You can rotate, you can touch and interact with the device in a very limited capacity. And then here we see another very similar device, but without have any kind of input-output capabilities. So these are designed by different manufacturers by following different design philosophies, but also economic principles which impact on the pricing and other factors. In this figure, you can see a futuristic vehicle where the users are provided with a very large screen and rich user interactions. So in this kind of scenario, we will most likely to see a hybrid approach where critical components are managed by embedded systems, and then there's a general purpose kind of computer that would interact with the user. The reason I use the general purpose kind of rather than exact general purpose, it is very likely that we will not be able to play high quality complex games on these devices, but it will do much more than a typical embedded system. So what we will see is a variant of a particular operating systems that are specifically designed to make sure that they are somewhat general purpose, but they are not general purpose as we use in our day-to-day life in a normal mobile or a tablet or a computer device. But they will provide wide variety of applications specific to that particular domain. So the domains that are where the price is not a big concern, we will see more and more dedicated operating systems will come to the market to support this kind of interactions. The reason that I talk about the economic price point here is developing an operating system for a dedicated domain is not cheap. And also not only development, but also the deployment and then the screens and everything, it increases the cost. But certain domains, for example, vehicles, adding these additional costs doesn't increase the overall price of a vehicle too much. So it can be absorbable, especially when you divided the R&D cost across a large number of vehicles. But it is unlikely that we will see this kind of interactions in other devices where smaller and cheaper, where you need to keep the price at a low point. But we already see that there are some vehicle operating systems, and there are operating systems for your smart watch, and then for televisions. So the more expensive devices that could afford to add a few bit of dollars or pounds on top of the price point could go into the direction of having dedicated operating system rather than general purpose, but it would be much more powerful and then have much more capabilities than embedded devices. So what I want you to understand is that even though we identify general purpose computers and embedded systems, that it could be more like a spectrum where you will see some of the devices will sit in between the two, which demonstrate the capabilities of both embedded systems and general purpose computers. This is another example where embedded systems and mobile devices and general purpose computers and gateways work together to provide experience to the end users. So this is called Hive thermostat, where you can control it by dedicated console, mobile applications, tablets, and more richer desktop or web applications. And then each of these user interfaces provide different experience, but together they provide the full, complete experience that users would like to receive from this particular IoT solution. In this slide, I wanted to show you what embedded hardware look like. So in the first figure, it is a printed circuit board where all the circuits are embedded. So this is more like a production level embedded hardware you can see. And then the other image, it is an Arduino controller, which is typically we use for prototyping and the research and development phase. So the internally how they work or the program is pretty much the same. But the Arduinos or the prototyping boards are not suitable for deployment, but developers are using these Arduinos or prototyping boards to first develop the prototype to see that everything is working, or does it make sense, or either any other sensors to be used or changing the actuator. So you can quickly and easily you can change things during the research and development phase. Once you figure it out, everything works fine as expected, you probably work with electronic engineers and specialized companies to actually print these circuit boards separately. The key difference is that when you're prototyping, it looks messy and looks bigger, but when you're printing out circuit boards or fabricating the boards, it could be very, very, very small than the actual prototype, because you are actually there's no cables, because everything is built into the circuit board. So that is a key difference in embedded systems in deployment phase as well as the development phase. So the microcontrollers are typically have very less computation capabilities. Clock speed, you are looking at a low megahertz range with a few kilobits of memory. And then they are very programmed specifically to perform a particular task. And also they're supposed to be low cost and then very small. So you can embed into any kind of device. In order to make use of embedded hardware, you need to develop embedded software. So typically, embedded software is designed to make efficient use of the limited resources. So you'll be very careful about how much your memory use and how to best utilize the limited memory you have, because it's very quickly the memory could run out. Especially if you have done some programming with microcontrollers, you might even realize that if you assign a lot of text into a variable, that could also overflow the memory. So even simple things that you don't even consider in a mobile application, like the amount of text or any kind of how long the variable is, become a critical factor when developing the embedded software. So embedded software is typically stored in non-volatile memory, the memory that is not lost when the device is not powered. It could be a flash or a ROM, which is read-only memory. So the difference is that if you want to change any kind of firmware running on a particular device, which is like a washing machine or any other device, you need to override the firmware. So if it is a flash-based memory or a storage, you can override. But if it is a ROM-based, which is read-only memory, you cannot upgrade the firmware. So those are the two options the developers have when you are developing the embedded software. So this software is developed in a minimalistic way that is only be sufficient to perform the particular task that is required by the system. And they typically comprise with a one simple program which you can deploy in the particular device. And then if you want to upgrade it, you need to completely flash it out and then put your new software. But you need to be careful when you are upgrading, because over the last few years, we have seen that companies trying to remotely upgrade this software, especially the firmware, and then become the embedded devices or the hardware become completely unusable. So this has happened for a number of different door locks, where the door lock can be opened over the phone, and then by touching the lock and things like that. But then you try to upgrade it, and then we call it, you brick them, or you become the device become a brick which is unusable. But the positive side is, actually, if you do it correctly, you can upgrade your firmware. When you come to the ROM, you pretty much cannot upgrade, so you are not going to break it or completely unusable. But if the program has done in a bad job, then it could be vulnerable for security risk, and it may not be able to upgrade the functionalities by upgrading the firmware at a later stage of the life cycle of the product, after you sell it to a customer, and then maybe after few years down the line, still the customer has to use the same functionalities without any kind of improvements. Previously, I briefly discussed about the operating systems within embedded hardware. That is an option, but you most likely to see embedded hardware without any operating system. But if the device is very complicated and specialized, it may contain some type of a real-time operating system which allows to manage system resources like processor, the networking, and other input and output. Operating systems typically provide flexibility to change the functionality and then be able to recover in some fashion than embedded software. For example, if you have operating system, you can upgrade it without flushing it out and then completely installing the new software. So that is an advantage, but it is not popular with the IoT developers at the moment because we previously discussed that embedded systems are supposed to be very small. So you don't want to give away your processing or computational resources to operating system. Rather, you would like to use it for your own application rather than sharing it or using it by the operating system, because you know that when you install a general purpose operating system in your computer, whether it is Windows, Linux, or Mac OS, it consumes large amount of resources to storage, the memory, and the CPU. Even you don't run any application on top of that. The same scenario applies to the embedded software, where we talk about kilobits of memory and very low range of megahertz of processing power. Even you custom develop an real-time operating system, it still takes some amount of resources. So most of the time you try to avoid any kind of using any kind of real-time operating system, but there are certain type of places where you might be benefited, or it's a trade-off. So the benefited and the advantages and the disadvantages. So the advantages is more than the disadvantages, then you probably end up using a real-time operating system. So for example, spacecraft, robots, and certain Wi-Fi access points tend to use these kind of real-time operating systems. It is also worth noting that operating system developers like Microsoft and in the Linux world, there are different flavors. So the Windows has the Windows embedded operating system, and then the Linux has their own variation. So they are used in a little bit more powerful embedded systems, I would say. You can see embedded Windows embedded in certain water management systems, industrial control systems, which are a little bit resource rich compared to the thermostat or something like that, which has very small amount of resources. However, if you decided to use an real-time operating system, that means it will increase the resource requirement for the overall system, and as a result it might increase the overall cost of the production as well, and then it also increase the complexities and things you need to manage. But even though we call these are negative aspects, sometimes the convenient that brought in, especially that not being able to completely flush and upgrade operating systems, allows to continuously upgrading certain functionalities or adding new functionalities. If that kind of scenario is more useful for your situation, then probably you will be using a real-time operating system. But it is not a decision that you take lightly because of the complications as well as the cost that it brings to the IoT product you are developing. Connected sensors are the third category of devices. We initially looked at it compared to the general purpose computers and embedded systems, embedded devices. So when it comes to the connected sensors, what we are looking at is very similar to embedded devices, but it is very much focused on sensing tasks. So they are very specialized devices to perform environmental monitoring or health conditions that are continuously monitoring certain aspects around it. Usually they don't have any onboard input-output capabilities. At the same time, it is unlikely that you are directly dealing with the devices as an end user. So most of the time these connected sensors can be configured or programmed to send the data to either cloud or a smart device or for a gateway, and then you pretty much interact with the gateway in order to get access to the data. So if your particular application is something that requires sensing capability, less focus on any actuation, you only need to monitor something, but you need to do it in a more efficient and a reliable way, you will probably end up developing a connected sensor. At the same time, because they are focusing on one task of sensing, it could be low powered, it could run for a long time, and then you probably don't bother about changing any firmware or any upgrades because you are focusing on a particular task, which is different from the embedded systems or embedded devices we discussed earlier. So technically, you can consider connected sensors as a class of embedded devices, where the particular class is only focusing on sensing. In a summarized fashion, the connected sensors are devices that are dedicated to collect data and provide the data to the IoT application, where the magic happens within the cloud or any other device which will consume the data as a data stream or a batch of data, not only from one device but from multiple devices, and then generate some valuable insight for the end users. You could find this kind of connected sensors in pretty much any domain, whether it is a smart infrastructure. You can deploy these kind of sensors even within the concrete when you're building things and measure different aspects of a building over time. Or it could be environmental sensors. You can deploy them around the cities to identify the noise or the noise pollution or the air pollution, or it could be something that you could take as a pill and then you try to monitor inside your body. So there are many uses of these connected sensors where the sensing is a key component of the IoT application. In this slide, I would like you to explore this particular IoT application or the use case. So in this use case, what they have developed is an IoT solution to help the patients, especially the patients with chronic conditions where they need to continuously take the medication, to avoid being forgotten to take their medication. 84% of the US healthcare spending is on the patients with chronic conditions, and then more than 50% of the prescribed medication are not taken by the patients as directed. So the common reason for that is either they forget, or either they may not convince of the medication's effectiveness and don't know whether they're actually doing any good for them, or they are also afraid of side effects or have any difficulties in in taking the medications, and also the rising cost of prescription medication. Out of these 4 challenges, this particular IoT solution is focusing on number 1, which is to help people to remember take the medication. So I would like you to go through this video. It's a small video that explain how these particular IoT solutions work and how these tiny little sensors are being designed to track whether someone has taken the medication or not. So now please go and watch the video. Connected sensors are largely deployed in groups. So you don't see typically someone deploying a sensor or a connected sensor one at a time. So you deploy large number of sensors. For example, if it is air quality monitors in your house, you probably deploy at least few different sensor nodes to cover the range of the house, maybe outside and inside, in different rooms, to get a very good idea about how these air quality changes in different geographical locations. Because sensors are very much contextual, because they are very much providing the information about the particular location in the most of the time. So because of that, deploying in a one sensor might be not enough to achieve the task that you are planning to achieve. But there are certain sensors or applications that deploying one sensor might be good enough. For example, in the previous in-body pill sensor, you only need one sensor to be embedded in your pill, which will tell whether someone has taken the medication or not. Further, in connected sensors, the amount of onboard computing you have is only sufficient to gather the data and transmit the data over the network. So there's a less of an expectation to do any more processing within the connected sensor node, which means that we can eliminate any kind of excessive computational resources and reduce the cost of a node drastically. So in a connected sensor, you only need a very basic processing unit with very little memory, power, and a communication receiver and a battery source. Most likely, you could also use energy harvesting techniques, rather than using solar or wind power, to power these small connected sensors, because they are not doing any complicated tasks rather than data collection and sending to the other devices. However, we discussed earlier in a different lesson where network communication is not necessarily cheap in terms of the energy budget. It consumes a certain amount of energy, and an energy that is quite higher than complex computation activities. Therefore, you need to be careful when you are employing these connected sensors in your IoT application to think about when you are sending the data and how much data you need to send. Can you send the data once a day? Can you reduce or aggregate the data within the connected sensor? Or you can activate the sensor when a particular event happens. So like if it is an intruder detection system, where you only need to send the data if the sensors detect some kind of motion. Sometimes these connected sensors could be developed in such a way that it can also receive a command from the control center. Such kind of two-way communication requires a certain amount of advanced programming, and then developing the architecture accordingly. But it could also help to reduce the energy consumption or develop more advanced applications. For example, if you have a sensor that you would like to change the sampling rate or the frequency of reading depending on the context which you cannot identify by the particular sensor. What I mean by that is, if there a sensor node has a motion sensor, then the context which that data need to be sent is already within that node, which means that the motion sensor says there is a motion, then you send the data. But if there are certain conditions that the particular connected sensor, which is dumb and don't know when to send the data and what frequency, you could develop a mechanism to send a command back to the connected sensor to change the frequency of the data. So this happens basically in a slightly complicated scenario where thousands of sensors may be deployed across the geographical field, and then each of the sensors are individually dumb, so they send the data to the cloud in a certain frequency. When the processing happens in the cloud, and then you derive the insights, which means that sometimes you feel that there are interesting information that need to be gathered. Maybe let's say the snowing start, and then the individual dumb sensors doesn't know whether it is snowing or not, because maybe it is only capable of sensing noise pollution or something like that, which does not have any kind of temperature or any kind of indication that whether it's snowing or not. In that kind of scenario, the centralized controller knows it is snowing because it has the full capability to other sensors or weather APIs. So now it knows it is snowing, and then sending commands to the thousands of noise pollution sensors to perhaps increase the sampling rate, if that is what you want to do. So that is a scenario where you might want to develop your connected sensors in such a way that you can send a command back and change certain some type of settings like frequency. Passive trackable objects are the last category of devices we identified at the beginning. So we already talked about the general purpose computers, we talk about the embedded devices, we talk about connected sensors, and then the last type of devices or a thing is passive trackable objects. So these trackable objects are not directly connected to the internet. It is there distributed across in a environment, and then the readers are potentially or the detectors connected to the internet. So depending on what kind of application or the technology we are talking about, they could be connected to the internet in different ways. For example, if it is a RFID tag or an NFC tag, the tags are just passive devices, and then when the tag comes to the area that there is a reader, the reader would identify the information inside it. It will detect it, read it, and then send it to the cloud or any other device for the further processing. So these trackable objects are, as you can see, are used for tracking. So they could use for tracking animals, tracking goods across the supply chain, across the geographically different countries. You can see they can move across different countries in different transportation mechanisms. So you can detect whether they've been loaded to the particular container, or whether they are in a ship, or whether they are in a ground. So the idea is that these objects can be independently, uniquely tracked across different geographical regions. Or it could be something like that you can temporarily wear in your wrist, which, for example, if you are going to a club or a particular venue which is restricted to public, or whether you have to buy a ticket or pay a fee or a membership, then probably they will put you a handband or something where you can use as a mechanism to identify yourself. Or previously we also noticed some small trackable devices that you can swallow in your body, and then it goes through your system, and then you can track their movement. You can see these RFID tags in different travel cards. So the Oyster card in London, one of the examples, or it could be wristbands, or it could be any device that you can put on your pet, which you can detect and locate if they go missing. And then it could be put on your keychain. If you forget your keychain, then you can actually locate them using these kind of technologies. So there are three variants of these technologies mostly and commonly used: RFID, NFC, and QR. In a different lesson about network communication, we have discussed these in a bit more detail. But at this point, what you need to know is these are the options you have if your particular IoT application requires certain tracking capability. The point to make is that because they are not powered devices most of the time, there are some active variations, but most of them are passive, which means they are not connected to power. They just respond to the reader. So the reader powers the tag, and then the reader can. Reader would technically emit a signal, and the signal would power the device temporarily, and then that temporary power allows to read what is inside the particular tag. These are passive and cheap. You can produce in large quantities and put them in individual items without increasing the cost of the item, and they can be reused as well. QR codes are the most basic way of giving a physical device a digital identity. So QR codes are basically two-dimensional barcodes. So you probably have seen barcodes in grocery shops and many other places attached to each item. One of the key differences between barcode and QR code is that a barcode is single dimension, so it reduces the amount of data which can be stored in that barcode. But because of the two dimensions, QR codes allows you to store more information, which can be read by any imaging device and extract the data encoded in the image, like a smartphone or a specialized QR code reader. Similar to RFID tags, QR codes rely on the code being mapped to more extensive product information in a database. Because of the limited capacity, it can hold limited amount of information. So when you are using in your application a QR code, you probably need to link to a more richer data repository where people can look up further information about that particular item. But because they are very thin, and then you can stick into any item, they are easy to be deployed very quickly and cheaper to produce in larger scale. Another technology that allows you to create trackable objects are beacons. So we usually identify them as Bluetooth low energy beacons, where it uses a variant of a low energy Bluetooth technology which emits signals, but it also includes a few packets of data where you can advertise a voucher or any kind of a discount you are giving to the customers. So they are widely used in that kind of context where you want to send out a small message like a coupon, and it has to be very localized. You don't want to send a message to the entire people in a large stadium or a shopping mall, but you want to reach out to the people who are coming into your store. Or maybe if you're a larger store, maybe someone reaching a particular part of a in your store where you are giving a discount related to a particular item or set of items that are located in a particular location. So the location or the context is a significant part of this beacon technology, or the usage of technology of beacons. You can advertise different things, and also these BLE or the beacon technology are being used to track pets and different items such as vehicle tags, keychains, things like that. But most prominent, or one of the first applications was in advertising in large geographical locations to contextually advertise certain items. So in this figure, you can see that there is a small advertisement which is very contextual regarding a drink put on in a particular restaurant. Bluetooth beacons can also be used in places like bus stations, where you can broadcast a particular set of information like a timetable. So anyone who's come to the bus station quickly browse through what is the next bus connected to the online. So it might be probably sending the link to the online, because beacon technology is not designed to provide live information to broadcast like what is the next bus, but it provides a link that you can go through quickly, and then the link will be updated real time, so you can get the real time information. But the link is provided by the beacon, but the beacon doesn't provide the information. So that is how this is beacon technology is expected to work. It gives a pointer for the people who are in the location nearby, so you can go and look up the more detailed information. So the detailed information repository has to go hand in hand when you are using beacon in your IoT applications. In this slide, I want you to bring a particular project into your attention, developed by Google, called Physical Web Project. The idea is that to develop technology to combine the physical and digital world together, and allowing people to interact with the two worlds, the physical and digital, seamlessly. So instead of broadcasting a simple ID, it will broadcast a particular web address, and then the web address pretty much show you an application where you can interact with. So you don't need to download or install any particular app on this link, but it is an online app which is custom developed to achieve a particular task. So I would like you to invite to go through this demo video where they have developed different prototypes explaining the idea behind Physical Web Project. At the time of the recording, this project hasn't taken off. It is not being deployed widely, but you can understand where the technology is heading and what is the vision that people are thinking ahead of time, how we will be interacting with the physical and digital world seamlessly. So this project takes the beacon idea but replace the unique ID with the web address, and then web address is connected to a particular application, custom a mobile application that does not require you to download anything. So you can just use it to interact with the physical world immediately. As we discussed in previous lessons, sensors and actuators are the device components that bridge the cyber world or the internet world and the physical world. Sensors convert energy readings from physical environment to numerical values that can be transmitted digitally. In contrast, the actuators convert digital instruction to mechanical actions. When it comes to sensors, sensors can be active or passive. Active sensors inject energy into the environment in order to detect changes of the environment. On the other hand, passive sensors detect energy that is already there. For example, motion detection system used in a store would use beams of light shown across the room to see whether anyone is breaking those beams, and then the sensor measures the loss of sight. In this case, the sensor is injecting energy, which is light, and then observing whether someone is breaking the beam. In a passive scenario, where you can think about a fire detection, where a sensor is looking for smoke, and then if the environment change, and then the amount of the NO2 increased in a particular environment, it will trigger the sensor, and then as a result it will trigger the actuators as well. A good example of an active sensor is where smartphones has the heart rate sensor, where you can put this your finger on, and then the sensor will emit a light, and then it will measure the changes in blood flow that indicates pulse. So you're measuring the changes in the light level by injecting a light and observing the changes of the environment. A good example of an active sensor is where smartphones has the heart rate sensor, where you can put this your finger on, and then the sensor will emit a light, and then it will measure the changes in blood flow that indicates pulse. So you're measuring the changes in the light level by injecting a light and observing the changes of the environment. In a previous lesson, we discussed about sensors and actuators from more technical point of view without looking at particular application scenarios. So over the next few slides, I would like to go through some commonly used sensors and to explain their common applications within well-known IoT products and services. So DropCam is a camera that contains a passive infrared sensor to detect motion. As we discussed earlier, mobile phones tend to have a variety of different sensors on them. So the accelerometers measure the acceleration based on vibration. They are often used in mobile phones and tablets to detect the screen orientation and present the UI in a landscape or a portrait mode. This is quite relevant to any IoT devices that has a screen, especially if it makes sense to provide the rotation capability. Some alarm clocks use accelerometer to identify the best time to wake the user. So the clock is placed on the mattress and it detects how people sleep and the movement of the sleep. So then they create some kind of a measurement of how good people sleep, and based on that and other patterns, the clock determines at what time the bell should ring. So these are very novel IoT applications. I'm not saying they are 100% working or even useful, but it is important for you to know these things so you can think in a similar fashion when you are developing your own IoT applications. So the gyroscope measures the angular acceleration, rotation around an axis. Typically, gyroscope can be used for more accurate movement measurements. So you can identify people, activities, running, walking, climbing hills kind of scenarios there. And also the gyroscope is also used in gaming scenarios to identify what kind of actions the gamer or the user is performing, and then change the game accordingly. And then also the GPS is a common type of sensor which perhaps could be used to track your pet, or you can track your children, especially very small children, as a safety measure. We also see the trend where some of the devices developers build specifically to monitor activities. Now they are being embedded in other commonly used devices like smartphones. What does this mean is that as an IoT designer or developer, you need to think about whether your product could be obsolete or whether the technology you built could be easily embedded into the everyday other devices where the consumers or the end users has to pay only once. For example, in a more concrete scenario, if the sensors in the smartphone can accurately measure the activity and then generate reports around that or the insights around them, then why would someone would specifically pay for a activity tracker? In that case, I'm not saying that activity trackers are not relevant, but in that case, you need to create a value proposition why the activity trackers are somebody needs to pay for activity tracker specifically, what it brings more to the table than what a mobile phone can do. This concept is valid for any IoT device because especially if you build something that which can be replaced by some of the existing devices, why would somebody would pay extra for that particular device? We previously discussed actuators in detail when we are discussing about the technology behind the actuation. But from the design point of view, I would like to suggest you to look at the actuation as a broad range of possibilities rather than the traditional actuation what we see like switching on and off or a light or changing, switching on and off of a door lock, or controlling the valve in your irrigation system. Particularly, one of the first images what you see is a small machine that generate bubbles just for fun. It's more like a toy, but that is also a type of actuation. There are a number of challenges in powering IoT devices. So when you're designing an IoT application, you need to think about how people would power the IoT device that you're designing. So you need to think about how it gets and use the power, and what are the implications of the user behavior on what kind of power sources you should use. So most of the embedded devices runs on batteries because they are portable. They seems to work well with small spaces. For example, you have like put a small battery, lithium batteries, size of like a Smarties on small devices. They can work without the access to the main power, so you don't need to wire any direct cables from the main power sources. Especially connecting to direct power may not be safe, easy, it could be expensive, or it could be laborious work, so it is much easier to connect into the batteries. So you have seen most of the motion sensors and some of the temperature sensors or some alarms, they all use batteries because you don't want consumers to go and put cabling around all over the houses or the places. So especially when it comes to the home devices, devices that personal devices people are interacting with, you probably end up with using some kind of batteries. But you could use direct power if there are something that you could traditionally people would plug in, like internet coffee machine, which pretty much everyone connected to a power. Then all the sensors and electronic power is not an additional thing, it's basically part of the traditional product. But if you are developing something new, something people would not typically use a direct current, then you need to think about whether you could use batteries or whether it makes sense. So when you're selecting a power source, it depends on the size of the sensor or the device as well. So if your device is small, you probably end up with using smaller battery source, like power source, like a small batteries with limited energy. Some of the devices could be able to employ some energy harvesting, such as solar or wind power, but it could be not reliable as well. So you need to maybe have some kind of battery sources. So if you're putting some sensors on a jungle or a remote area, you could use solar power or wind power, but then you need to have a battery. So during the daytime or when you have the wind, it will charge the battery, but the battery will power the particular device. There also could be opportunities where you can generate enough power from the user's interactions. So for example, when the user press a switch, it could generate tiny amount of power to generate some electricity that could power a small tiny data transmission. We call this electricity piezoelectronic electricity. You need to also think about how you are going to report the battery status or energy status, or whether you need multiple battery sources or multiple power sources, like you have a direct power And then you could also, depending on the battery, for example, if you like critical things like fire alarms or any other security systems where you have the main power, and then if it is somehow disconnected, then the backup battery kicks in at least to for some number of hours, so it can maintain the security or the mission critical process. And also you need to think about when you are going to do the communication, which consumes a lot of energy, so you can do intermittently to save the energy. And also if the power source changes or the battery get depleted, you could also think about whether you want to reduce the communication or any activities that would further deplete the battery quickly, while the user or anyone who is responsible for the device would change the batteries or do the charging